Hi everyone, this is Kalyan Kumar and welcome once again to Chemistry Universe. And this is the second edition of Aryl Halides. The first one that we talked about was a brief introduction and we talked about ARSN2. And I had told you that Aryl Halides basically show two mechanisms, ARSN2 and the second one is Benzyne. And this one coming up is part 2 of that series and this is titled Benzyne Mechanism. Now in this video what we will talk about is what is this Benzyne mechanism, what is Benzyne, what is the nature of Benzyne, is it aromatic or not aromatic, because since it is formed from benzene so we need to understand that. And then we will do a couple of reactions of Benzyne mechanism. This is going to be an extremely short video, so make sure you watch it in one go, and as always make notes while watching this video. Don't watch it like a movie. Wherever you need, pause the video, make notes. If I ask you a question, pause the video, answer it on your own, and then check and play back the video. So with that, let's begin part 2, Benzyne mechanism. So here we go. So let's understand what is this Benzyne mechanism. Now, in the presence of a strong base and the substrate with unactivated or deactivated ring, Benzyne mechanism is followed in nucleophilic substitution of aryl halides. Now, I had mentioned this in the last video that activating or deactivating groups depend on the nature of substitution that are taking place. So, if the reaction happening is nucleophilic substitution, then withdrawing groups are activating groups and releasing groups are deactivating groups. So Benzyne mechanism is followed when the aryl halide has either a deactivating group or it has no other group other than the halogen, meaning it is neither activating nor deactivating, it is unactivated ring. So both in unactivated cases and deactivated cases, Benzyne mechanism is followed. So you have chlorobenzene treated with a strong nucleophile like OH minus, strong base also, and temperature is 300, pressure is 10 atm, and you will find phenol. Now if you notice, I have used the word strong base, and you might wonder why have I used base and not nucleophile. Well, you will be able to find this out when I show you the mechanism. So this is the mechanism. Step 1. So here you have chlorobenzene. Now I have shown the two ortho hydrogens, but they were anywhere there. So the fact that I didn't show them before doesn't mean they were not there. Now let us take a different nucleophile. Let's take amidine NH2 minus in the presence of liquid ammonia. Now this NH2 minus grabs this H, the ortho H, and this bond goes to the carbon atom and you get a carbanion. Now this carbanion is very different from the carbanion that you saw in ARSN2 simply because this is an sp2 orbital. And when I show the arrow like this, it means the sp2 orbital is the one which has the lone pair. So the benzyne is formed because of the sp2 orbital. So this is lone pair. Now this minus cannot resonate, remember. It is not perpendicular to the plane of the ring. It is not parallel with the pi bonds. It is in the plane of the ring. So this can't resonate. So it's different from the one that you saw in the case of ARSN2. In step 2, what happens is this carbanion attacks the carbon that has the leaving group halogen and Cl goes off, and this is what is benzyne. This is benzyne for you, okay? So it's looks like an alkyne. Perhaps the name benzyne is derived from there. And then in step 3, the benzyne reacts with amidine again. Remember, this amidine has taken the proton and become ammonia. So another amidine comes and attacks one of the carbons of benzyne, and the bond that has been drawn outside breaks and goes to the adjacent carbon, and you get a negative charge there and the nucleophile gets attached. And the last step, this one grabs a proton from ammonia, the solvent, and you get aniline. Remember, NH3 gives a proton, becomes NH2 minus, and of course, now you have aniline. So you started from chlorobenzene, ended up with aniline by using NH2 minus, a nucleophilic substitution on aryl halide. Now let's understand what is benzyne. Now remember, before I go back, let's see this. This is the RDS. That means this grabbing of proton by this base is RDS, which is why I've written base here. Because first thing that NH2 minus does is behave as a base. So if you don't have a strong base, it doesn't matter if you have a strong nucleophile. If you don't have a strong base, it's not going to work. So let's look at benzyne. Now this is the benzene ring. And this carbon is sp2 hybridized. It has got 3 sp2 orbitals, equilateral triangle. The carbon that is adjacent to it is also sp2 hybridized and it's got 3 sp2 orbitals. One of them, let's say this one has the hydrogen and this one has the halogen. So you got a hydrogen and a halogen. And there are p orbitals which are perpendicular to the plane of the ring. And these are the ones which form the normal pi bond of benzene ring. Now what has happened is that when the base grabbed the proton, the electrons of this bond went towards this orbital. This became minus. Then this attacked in the next step and this left. Now what has basically happened is that this has lone pair. This orbital is empty. So the pi bond that is formed, which is drawn outside the ring, is the pi bond between two hybridized orbitals, one filled and one empty. Now here I would like to submit that when we do chemical bonding, we are already always told that pi bond is always formed with unhybridized orbitals. Unhybridized p orbitals, unhybridized d orbitals. This is a unique example where a pi bond is formed between two sp2, that is hybridized orbitals. The second thing that you need to understand is in a pi bond, the two orbitals are parallel. As much parallel they are, as much close to energy they are, perfect would be the pi bond. In this case, these are at 120 degrees. So the pi bond formed between these two is not effective enough. Formed, even though it is formed, but not strong enough. So because of the fact that it's not strong enough, this pi bond is going to be a weak pi bond, weaker than the pi bond of the benzene ring, number one. Number two, since it is in the plane of the ring, remember it is sp2, it is in the plane of the ring and not perpendicular to the ring, just like the pi bonds of the benzene ring, therefore it cannot resonate. Meaning that those 3 pi bonds of benzene ring will keep resonating as they were resonating in benzene, which also implies that benzyne is aromatic. So this extra pi bond has not disturbed its aromaticity because it is simply not involved in resonance. And remember, in figuring out aromaticity, we only look at those pi electrons which are involved in resonance. And those are the ones which are counted for 4n plus 2. All right. So what has happened is this bond has gone here. This Cl has left. This is filled and this is empty. And there's a pi bond between them. So in benzyne, the 2 carbon atoms having a triple bond between them seem to be sp hybridized. But sp hybridized atom can never be a part of a ring since its geometry is linear. So you can never have an sp hybridized carbon in a ring. Perhaps a very big ring may be able to accommodate, but even then it's going to be a tad difficult. But yes, it's possible. But otherwise, you can never find an sp hybridized carbon as a part of the ring. So in a ring, you can have maximum sp2, sp3 is of course there, but you cannot have sp. In fact, the 2 carbon atoms having the triple bond are sp2 hybridized. Now the third bond is weak, sideways overlap, between a filled and an empty sp2 hybridized orbital. This is a very rare species in which hybridized orbital form a pi bond. We discussed that. That is why this bond is shown separately outside the ring so that it can be differentiated from the ordinary pi bonds in the ring. So I think you understand why we drew this pi bond outside. Otherwise, generally we draw a sigma bond and two pi bonds, one on top of the other. But here we have a sigma bond in the middle, one normal pi bond inside the ring, and this weird pi bond outside the ring. That is how benzene is drawn. Since the first step is RDS, that is the one in which the proton is being taken out, the leaving group does not influence the rate of the Benzyne mechanism. And since the first step is the RDS, it is a bimolecular reaction as well as its order is 2. Now, if you ever want to find the reactivity of various halides, don't look at the leaving group ability, but just look at which makes the carbon or rather the H more acidic. So if suppose I have these, now ask yourself which will make this H acidic. Now to do this, you only have to use inductive effect. Now this is very, very important to understand. You have to use only inductive effect. That is because this H, when it is left, you get a negative charge like this one, this lone pair. But this lone pair cannot resonate. It's not in the p orbital, right? Whereas the resonance, the plus m of F is always going to be in the p orbital. So when this comes and let's say this pi bond goes here, it is basically going to the p orbital. So even if the resonance of this brings electrons to the p orbital of this carbon, the minus charge that you have because of the loss of proton is in the sp2. This has nothing to do with this. So whenever in Benzyne mechanism you try to decide, you must understand that the acidic H that you're looking at is in the sp2 orbital, and only one effect should be operative here, that is inductive, because inductive occurs through sigma bonds. So inductive will affect the acidic strength of H, not the mesomeric effect. Therefore, the order should be this, because fluorine being more electronegative will make the ortho H more acidic than chloro, than bromo, and than iodo. Now, one of the differences that you'll find between the products of ArSN2 and benzene is that in the first, the nucleophile attacks only the carbon with the leaving group, while in benzene, once benzene is formed, the nucleophile can attack either the carbon which had the leaving group or the adjacent carbon. Again, something to understand here. Benzyne mechanism. Remember, the two carbon atoms having this weird outside triple bond. Now, the nucleophile can attack either the, let's say one of them is carbon 1, the other is 2. It can either attack 1 or it can attack 2. But remember, the leaving group was only attached to one of them. Let's say carbon 1 had the H and carbon 2 had the leaving group. So the benzene is formed between carbon 1 and carbon 2. But when the nucleophile attacks, then on the benzene, it can either attack carbon 1 or carbon 2, which means it can attack the carbon which had the leaving group or its adjacent carbon. So if it is like this, you have chlorobenzene forming a benzene like this. Now the nucleophile can attack either this, the original carbon having the leaving group, or its adjacent one. And whenever in a nucleophilic attack, the attack happens on the adjacent carbon to the leaving group, it's called sine substitution. And remember, we saw sine substitution even in NGP. If you say for example, you have Me here and Me here and NH2 here and Br here, and there's an H here and there's an H here, and you have a nucleophile coming in. Let's say I use Finkelstein reaction, NaI and acetone. So what will happen? This I minus will generally replace this Br and come from the opposite side. It will show SN2. But the NGP of this would make a ring here, right? So if you look at the NGP, you have NH2 forming a ring with this, having a plus here, H here, and the Br is gone. Okay, so let's remove this. So now the nucleophile can either attack this carbon or it can attack this carbon, since both carbons are similar. So whenever it attacks the adjacent carbon, we call it sine substitution. Now, if a releasing group is present, then the major product is judged by how much it stabilizes or destabilizes the negative charge that is generated after the attack of the nucleophile on benzene by inductive effect only. Again, remember this. I've told you this before. Remember, benzene is formed. The nucleophile attacks the carbon. The external pi bond shifts to the other carbon and that carbon becomes negative. Where does the negative go? It goes to the sp2 hybridized carbon orbital, not the p orbital. That means if there is any group attached along with aryl halide, then its mesomeric effect will not be seen, because its mesomeric effect will not affect the stability of this anion, because this anion is in the sp2 orbital. It's not in the p orbital, and mesomeric effect works only with p orbitals. And therefore, you only have to check the inductive effect of the group attached. And how will you decide that? Well, let's say, for example, you have benzene between 1 and 2, and there is a carbon having a releasing group which is closer to 1. Now, if it attacks 2, the benzene pi bond will go to 1. And if it attacks 1, the benzene pi bond will go to 2. You just have to check which of the two minuses formed is stabilized or destabilized by this group. Now, if it is showing plus I, obviously it would not like to have the minus close to it. Meaning it will not try to have the minus on carbon 1, it will prefer to have it on carbon 2. So the only way you can get minus on carbon 2 is when the attack happens on carbon 1. Similarly, if you have a minus I group, it's the reverse. The attack on 2 will be preferred because then the minus can go to 1, which is closer to the minus I group, and that would be stabilized. So say, for example, you have this. Now, whenever you have a group which releases electrons, remember benzene is followed, and you have to first of all make the benzene which is most stable, or rather the benzene which can be formed by the most acidic H. Now here, of course, there is only one H. So it will form benzene with this. Now where do you think the nucleophile will attack? If the nucleophile attacks here, the minus goes closer to Me, and we just have to look at the inductive effect. If the OH minus attacks here, the minus goes onto the meta of Me. Again, you have to see only plus I effect. So if you have to see only plus I effect, can you see the minus would like to be far away? Meaning the attack will be ortho. Try this. Now first of all decide which H is more acidic. And again, this acidic H has to be decided by only and only inductive effect. So Me has plus I, so obviously it will not like to have this H being removed. This H will be relatively more acidic. Of course, you will get two benzynes. One benzene between these two and another benzene with this one. Now, of course, I've shifted the position of double bonds, doesn't matter. Now, obviously, which is formed more? This is major. Okay. Now, out of this major, where will the nucleophile attack? If the nucleophile is OH minus. If it attacks the meta, minus will go to para. Isn't that far away from Me? Wouldn't that be more stable? So the product is meta product. Whereas, if you look at the first benzene, which is of course minor, and the OH minus were to attack, if it attacks the ortho, the minus will go to meta, which is far away from Me, which is better. So the ortho product is major. Now I want you to use the same logic and figure out the para. Pause the video, make it on your own and tell me. Obviously the benzene can only be formed either from the left side or the right side, which is the same thing. Where do you think the nucleophile will attack? If it attacks the para, minus goes to meta. If it attacks the meta, the minus goes to para. Where would you like the minus to go? Far away, para. Meaning the attack will happen on meta. Remember, the minus going to para doesn't mean the attack happens on para. Minus going to para means attack happens on meta. and the product is the meta product. And that finishes this short video of Benzyne Mechanism. So that's it, folks. Part 2 of Aryl Halide is over. And so we have done ArSN2, we have done Benzyne. This covers Aryl Halides in total. These are the two nucleophilic substitution reactions Aryl Halides will show. But there is one more nucleophilic substitution which is not of Aryl Halides, which is of benzene diazonium chloride or diazonium halide, which is ArSN1. And since we are doing a nucleophilic substitution, I thought we might as well do ArSN1 and finish off nucleophilic substitution on aryl systems. For that, I'll see you in the next video, part 3. Till then, it's goodbye and have a nice day. And thank you for watching this.